Hi, this video is about comparing three standardization methods for getting your relationship between concentration and signal. The three methods are external standards, which are often called calibration curves, standard additions, and internal standards. I'll talk about what each of these three things are and give you tips on when to use them. So in our fantasy, we really would like to be able to only measure the samples. That would be the least amount of work. The samples are what we care about. We want to just measure them, get their concentrations. But in reality, you have to have something to compare them to. You have to get a proportion between the concentration in a sample and the response that it'll give you. And so we have these things called concentration standards. Thus, these are called standardization methods. External standards is very common, fast, and easy, and is probably the one that you're familiar with. So the reason why this is so easy is that it only requires a few solutions past our fantasy of only analyzing the samples. The standard solutions are prepared using analyte, that is the standard, and they're separate from the unknowns. That separation, where your unknown sample is a different solution from your standards, is what leads this to be called external standards. There are single point standardizations, where you get the response of a known sample. You calculate the proportion, which I mean is the proportion between response and concentration, and then you use that for all of your unknowns, assuming that it applies to all of them. Multi-point standardization is getting the response of several knowns. You calculate a proportion from that, and as you can see here in a calibration curve is a multi-point external standard. Then you can apply this to a range of unknowns, and the range of unknowns for which this applies is the range that goes from the low end to the high end of that calibration curve. Nothing below the low end and nothing above the high end. Now, what's the advantage of one versus the other? Well, if you have a single point standardization and you make a mistake in that one known sample, that mistake is going to propagate through to all of the unknowns that you analyze, and that's a systematic error. However, with multiple point standardization, if you make a mistake in one sample, then that could be canceled out by other samples in your multiple point calibration curve. Also, it's more reliable for multiple concentrations because you've checked that that proportion is actually true over the whole range of concentrations. Okay, calibration curves. Having a good calibration curve simply isn't the end of the story. I'm going to walk through a couple of things that we all have believed and maybe still believe at some point about having a good analytical method. The first is that r squared equal to 1 or very close to 1. All this tells you is that it's a linear calibration curve, which is really important. Maybe you also have an intercept of 0, which means that your blank was good. And maybe you also did a calibration check and it gave you the right answer for that known concentration. So everything is great, right? You have a right answer. Well, not necessarily, okay? No, just because it's linear and you have a 0 intercept and you got your calibration check, which you probably made in the same matrix distilled water as your calibration curve, doesn't mean that everything is fine. So the first problem that's common is matrix effects. The matrix is everything in your sample other than the analyte itself. Matrix effects are when the analyte is going to change its response according to different matrices. The plot here shows the signal for perchlorate ions using reagent water, which is your nice steep curve with high sensitivity, which is probably the distilled water that you would use in lab to make your calibration curve, and groundwater, which is what you are actually interested in. And in groundwater, you see that it's got a much lower slope, much lower, 15 times lower sensitivity. So that's a matrix effect when you have this different slope. How do we check? Well, the first thing is make the calibration curve in the two different matrices and compare the slopes. And if they're different, then you do have matrix effects. Or we can do spike recovery. Spike recovery is a method to detect matrix effects. I have a whole other video that gives you details, but here's a brief summary. The first thing you do is read your unknown unspiked sample. Let's just say it gives us that blue dot right there. Then you're going to add a known concentration of standard, C added. So you're going to move that concentration over by a known amount. And what you would expect in a good result here is that the signal would increase the same amount that your calibration curve predicts it would. And so your sample reading after the spike, the concentration spiked, is going to land on this green dot. But in our example here with perchlorate and groundwater, because the groundwater suppresses the signal of this, what's really going to happen is that you're going to get just this tiny little rise in signal. And you don't know where the concentration should be, so that tiny rise in signal is going to land this red dot right there on the left-hand side, which is a very small increase in concentration according to the calibration curve, versus what you think you should have by what you've actually added. The The reason why spike recovery is so great is that the spiked and the unspiked samples here have the same matrix as each other because their matrix is the matrix of the sample. You're going to do a calculation of concentration spiked minus concentration unspiked divided by the concentration of added. If you get a poor recovery, something that's not 100%, then that means that you have matrix effects. You always have to measure your sample before you spike it, and you always need to know the volume of the sample and of the standard and the concentration of the standard in order to calculate C added. To fix matrix effects, you really have two main options. The first is matrix matching. That's where you make the external calibration curve in the same matrix as your samples. That requires you to know what the matrix of your samples are and to be able to create that synthetically in the lab, which might be hard or impossible. The other option is to do something called standard additions. I'm about to get into that in pretty gory detail here. And here, with standard additions, your matrix is the actual sample itself. You're going to add a known amount of analyte to that sample. It's essentially the method of spike recoveries, but now instead of looking at it as, do I get the amount of response I'd expect from my calibration curve, you're looking at it as, can I use the amount of response I get in my sample to tell me something about the proportion between response and concentration? So to summarize, standard additions is adding a known quantity of analyte, which is the same molecule. Your standard here is your same molecule as your analyte. You're adding that into the unknown. Because it's added to the unknown, your standard is in that same matrix as the unknown analyte. Pro is that it does deal with matrix effects. The con here is you have to do this with every single sample because your samples might have different matrices. You have two choices to make, single point versus multi-point. If you have the sample, the time, and the money, multi-point will be better for the same reason that if you make a mistake with one of these standards, other standards can help average that mistake out. And the other thing is that you have to choose between variable volume and constant volume standard additions. And they'll tell you right now that if your analysis consumes solution, like you're burning in sample in an atomic absorption instrument, or you're injecting it into a chromatography instrument, and you can't get it back, or maybe you put it in a cuvette for UV-vis spectroscopy, but you can't pour every single drop of it back out of the cuvette, then you should really do a constant volume standard addition. The other thing is that if you needed to have a variable volume standard addition, you can't dilute your sample too much. You need to have that highly concentrated standard that you're going to use a very small volume of. So if you don't have an adequately concentrated standard available, then you won't be able to do variable volume. So I'll start with single variable volume standard additions. Step 1, get your original sample that has not been altered in any way. Measure out a known volume of it. Get your signal. You don't know the concentration yet, but you've got the signal. Then you're going to add a small volume of the highly concentrated standard to this unknown. You make sure that you know the volume of standard you're adding and its concentration, and you measure the signal of the spiked sample again. You'll notice under the second beaker, which has that deeper color for more analyte, that we do have dilution factors due to the fact that your standard is diluting your solution just that little bit. Now you're going to set up a proportion between the signal of the unspiked sample and the original analyte concentration, and on the other side the signal of the spiked sample and its concentration, which again has the diluted analyte concentration from the original sample and the diluted concentration of the standard. So make sure you're accounting for those dilutions. That dilution should be small. You need to dilute it much less than 5% of the original volume. And I have a whole separate video with an example with numbers for this. For multiple standard additions with variable volume, you're going to keep spiking it with that same amount of standard multiple times and keep reading that measurement. What you're going to do next is to make a plot, and the plot will look at first glance like a calibration curve. The only difference is that your calibration curve, your x-axis and your y-axis will be different. So on the x-axis, you do the concentration of the standard times the volume of standard divided by the original volume of the sample. So as your volume of standard increases, you're going to be moving that over on your x-axis. The y-axis is the measured signal, S, and you again have to deal with dilution here. So that's times the total volume, V0, of the original sample plus the V standard added at that particular data point, divided by the original sample volume. And what will happen is your x-intercept here is going to be the analyte concentration. So in the plot right now, we've got an x-intercept of about minus 2.9, and that means that you have a 2.9 original concentration. When you're doing something like this, I want you to know this is a good example of a standard addition plot. You want to increase the original signal of your sample, which here was roughly 2, by a factor of at least 1.5 up to 3 times greater signal. And so that got up to a signal of about 6. Just making sure that you don't dilute the sample too much. You want less than, say, 5% total dilution for this to work well, because you have to keep that matrix identical to the matrix of the original sample here. I have another video which has a worked example of this multiple standard addition approach, so you can see how exactly to do the math here. For constant volume, what you're going to do for single addition is prepare 2 solutions, each of which have the same V0 initial volume of your unknown. You don't know Ca, we'll get there. To one of them, so that's your single standard, you're going to add a known volume of standard of a known concentration. And now it does not have to be so concentrated. As long as the volume fits in the flask that you're using, you're okay. Both of those get diluted to the same total volume, and if you look under these 2 flasks, you can see that the concentration of analyte, Ca, and the concentration of standard are both receiving that dilution factor of their original volume divided by the final volume. Again, you're going to read the signal of both samples, and we're going to set up an equation with a proportion between the signals and the concentration, where that dilution factor appears in the formula. To work with this, it's not that hard. You measured those 2 signals, so they are known from your instrument. You recorded the volumes that you used of the original sample and standard, and the concentration of the standard is known. It's a standard after all. And so you're just going to plug those numbers in and rearrange to solve for the concentration of analyte in your original sample. For multiple standard additions, you take the same approach, but now you have additional standards. So let's just say you have the original sample plus 4 plus 4 standards, and so that's 5 flasks, all of which receive the same amount of unknown. In this example, 5 milliliters. Then you're going to have one flask always has no standard added to it. That's super important to remember that one with no standard added to it. And then you have increasing amounts of standard added to the other ones, and they all get filled up to that same total constant volume. So constant volume standard additions is referring to a constant total volume. All right. Now what do we do? The next thing to do is to make a plot. This is the graphical method of standard additions. For constant volume, your y-axis is the signal, either the signal of the unspiked sample or the signal of the spiked sample. Your x-intercept now is not exactly the analyte concentration like it was with variable volume. Now you're just going to use that x-intercept to get analyte concentration. And there's 2 things here. The first option is that your x-axis is plotted as the volume of standard that you added. In that case, the x-intercept, which is here roughly minus 1.7, is saying the amount of analyte in your original sample is equivalent to the amount of analyte in 1.7 milliliters of standard. And so now you have to use M1V1 equals M2V2 to set up that proportion and solve it as is described in the blue box. The other option is that you could plot the x-axis not as volume of standard, but as final concentration of the standard, that spike that you kept adding. And so you're accounting here for the dilution of your standard concentration. And now in that case, the x-intercept is used to obtain that diluted analyte concentration. So you can see that in the purple box for the x-intercept. Now, standard additions dealt with matrix effects. The other major problem that you can encounter with external standard calibration curves is issues with reproducibility. Now, what do I mean here? Suppose you measure 2 samples, sample 1 and sample 2, and they give you these 2 plots. Sample number 2 has a lower intensity, and so one could be led to believe that the concentration in sample number 2 is less. But does it really have less analyte? Maybe. It really depends on how reproducible your method is. If your method is not reproducible, we can't be sure that a lower signal means a lower concentration. This is common if you're doing chromatography, where you're injecting microliter volumes of sample, especially if you're doing that injection by hand. You're usually not as good as an auto sampler. And it also happens a lot if you have a lot of sample processing steps, things like heating your sample or condensing it, filtering it, reacting it with something else. How do we know if the lower signal is not perhaps due to injecting a lower amount of sample in chromatography or due to loss of your sample because it stuck to the filter or evaporated away or didn't fully react? Well, one way that we can know is by adding a standard into internal your solution. So if we have that first sample number 1, we have this intensity of analyte. I just copied this from my last slide. If you put that standard in, you can get an intensity for that standard as well. And notice that these create two different peaks. You have to be able to distinguish your standard from your analyte here. So internal standards is using a different molecule from your analyte. Now, when I go and I analyze sample 2, to which I've added the same concentration of standard that I added to sample 1, if I get a plot like this, and both of them have gone down in the same proportion, then I know that, yeah, it's just a reproducibility thing. The relative amount of analyte to standard stays the same, and so those two samples have the same concentration as each other. So to summarize, internal standards is adding a standard that is different from the analyte whose concentration is known, and it's going to be easiest on you if it's known and you keep the internal standard concentration constant. You're going to track the signal of that internal standard as a reference. The best standards are different from your analyte, but similar enough to your analyte that they behave similarly in your instrumentation. You also have to make sure that you distinguish your analyte from your standard. If you're doing UV-Vis molecular absorbance spectroscopy, it's probably A, reproducible enough that you don't have to worry about this, but B, has really broad peaks, really broad absorbances, where you may have trouble telling two molecules apart. So, like everything else, we have single and multiple point internal standards, and I'll start with single. You begin with a standard sample. You make a mixture where you know the analyte and the standard concentrations, and remember that brackets here, bracket notation means molarity, so that's your concentration. You're going to measure the signal intensities of both. And then you're going to use the equation on the right-hand side, which is just a proportion between intensity and concentration for both analyte and standard, to calculate a relative proportion, or response factor, F. Okay, so step 1, standard sample to get the response factor. Step 2, now you can have an unknown sample. To that unknown, you still have to add the known concentration of standard. You're going to measure its sample. Now you're going to have that measured intensity of analyte and intensity of standard. You're going to have the known response factor from step 1 and the known concentration of standard you added. And now with that unknown, your task is to calculate the unknown concentration of analyte. With multiple point internal standards, the real essence here is that you should really check that your calculated response factor is true over the whole range from low to high concentrations of samples that you're interested in. It might change with concentration. So you make a series of samples with known analyte concentrations. Again, known and constant internal standard concentration, measure their signal intensities, and make yourself a calibration curve. Here's an example of 2 calibration curves, where xylose and glucose sugars were measured in reference to a fucose internal standard. And that fucose internal standard was present at the same concentration in all of them. To make that plot, your y-axis is a ratio between the two signals, so intensity of analyte over intensity of internal standard. Here, the blue curve was intensity of a xylose peak over intensity of that internal standard fucose peak. Your x-axis is your concentration ratio, concentration of analyte over concentration of standard. What you basically are doing here is rearranging that internal standard concentration from the prior side. So I cross-multiplied, and I got the intensity of standard on the bottom left, and I got the concentration of analyte on the top right. So the intensity signal, basically, ratios are your y, your f factor is your m, your slope, and your x is your concentration ratio. If you're good and you use the same concentration for standards, that bottom of the right-hand side, the concentration of S, can go right in with your slope factor, and you can simply plot it versus concentration of analyte. Now, what I want to point out to you through the use of the F prime here on this factor is another really nice thing, which is that you don't have to remember a particular equation to work with internal standards. As long as you know you're getting a proportion between signal and concentration of analyte and standard, it doesn't really matter where you put the F. as long as you set up your proportion, you calculate F using the same setup as you use that F to get an unknown concentration. So to summarize, I hope that through watching this video, you've learned that multi-point standardization gives better rigor, but does require more effort than single point standardization. I hope you've learned that a calibration curve, like we tend to call them, is really a multi-point external standard approach. Your standard is your analyte, but it's in a separate solution from your unknown. You should really check for matrix effects using the method of spike recovery that tests whether the matrix of your unknown sample is going to match the matrix of your calibration curve. If it doesn't match, if you have poor spike recovery, you probably have matrix effects or you didn't do your spike recovery right. And so you're going to either need to matrix match that sample and calibration curve of external standards, or you do the method of standard additions, where more analyte is added into your sample as your standard and helps you build that signal versus concentration response in the sample itself. Lastly, if you have reproducibility issues, you should use internal standards, which is the only method of standardization that I've talked about, where your standard is a different molecule, similar to, but different from your analyte. And you're going to use a response factor between your analyte molecule and that standard to see how their proportion stays constant, which helps you deal with reproducibility issues. I hope you find this helpful, and thanks for watching.